Can you hear me? Okay. Good morning. All right. One guy. Good morning. Oh, hey, Perth. Now you're on Zoom. Okay, good. All right. Let's continue. So I'll tell you where we start for midterm today. And then Monday will be next stuff. So today we're going to finish midterm material. No more midterm stuff. But in any case, I mean, we went through some of the questions yesterday. It's mostly it's mostly from the back, so don't be scared too much. So know your linear spans, linear dependence, um, dimension of kernel, dimension of image. Okay. What else? How to solve subspace, how to solve vector space. Yeah. I mean, we won't ask you to go through the axioms, so you won't see that, but definitely show something is a subspace. You need to be able to check it. Okay, any questions from here? All right, if you have a question, just tell me. All right, so last time we talked about isomorphism. Let me remind you. Isomorphism just means invertible. Okay, and we want to show that so invertible, meaning you go from V to W and you can go back by a T inverse. All right. So yeah, so we need both. Yeah, we need both. So you need both injective and surjective. Let's see why. Well, okay, whatever. We'll talk about it. How about the map X cube? Is this invertible? Is it injective, surjective? Here and in the chat, can people tell me what's going on? Is this guy injective, X cube? Yes or no? Yes. Anybody else? So is it injective? Yes, no, no, yes. All right. Is it surjective? Yes, no, no, yes. So as a map from R to R, is this guy surjective? Yes, no, yes, yes. Okay, is it invertible? What about people in the chat? Yes, no, no, yes. Is it invertible? Oh man. Okay. So it's not invertible. That's an example. I put it there as an example to show that you need linear map. So, uh, all right. How shall I say this? Why not invertible? Any ideas why it's not invertible? Let me write this more clear. So invertible means that there exists some g of x, so that g of x, x cube from R to R, mind you, is x. What could be a choice of such g? Right. So if you put that guy, so if you let g of x to be x 1 over 3, well then what is minus 2 of 1, 3? It's a complex number. -1 to the 1/3 to 1/3. This is e pi ei pi third. So this is complex. You cannot take fractional powers of negative numbers. Question? Yeah. Oh, because you have three choices here. So you so how do you say this? So I have to think about this. So how can you show contradiction here? Yeah, let me think about it. Okay. But yeah, be careful when you take yeah. So as a function from R to R, you're in trouble. So be careful when you do that. I mean, I could like, if you don't like, okay, here's a, if you don't like the one, so okay, let me think about this. Okay, I will come back to it later. But the point is, you cannot take fractional powers of negative numbers. I think, okay, damn it. So, yeah, be careful when you do that. So, for example, -1/4, that's also problematic. But I think in calculus, they sort of define, like you said. Okay, let me not go too deep into this. We can talk about it after. But okay, you know what? X cube in a way is invertible because it's strictly increasing. So this is always the case. Okay, I shouldn't go too deep into this. I will find you some other example later. It's fine. But yeah, okay. Yes. So we have to show this. So assume your guy is invertible, get injective and surjective. All right, first we get injective. What do I want to say? Yeah, so you give me two vectors, v1, not v2. We assume that they're equal. Right, so if I give you that tv1 is tv2, and you know that T inverse exists, how can I get that? How can I get a contradiction? What's the, yeah, you just do what? Right. So you take inverse of both sides, right? That's what you wanted to say, right? Oh, no. We're assuming that it's invertible. We want to show injective. Okay. Well, okay. I mean, we're doing the same thing. Then you can take T inverse of this. Like that, right? Then, yeah, you get V1 minus V2 is T inverse 0. And I'm going to talk about it in a second. This is also linear, so it's also 0. So you get this. But well, you could just do it here. You just take both sides. And you know, and you get this. But yeah, we'll come back to your proof for the other direction. Any questions? All right. Okay, surjective. So why is it surjective? So what do I have to show? So for every W in W, yeah, so let's parse this out. So you look at the image and you give me any W. I have to find you some V so that T of V is W, or I call it X. And right. How shall I say this? Right, but T inverse exists. Okay, T inverse exists. So you can take T inverse of W. And we just call this, X. So this is our X. And then, yeah, you just act with T on it. So indeed, you get W. So all W are in the image of T. So that means you're surjective. Is that okay? So we showed that if you give me any W, we showed that this is a subspace of image T, which itself is a subspace of W by definition. So you get that they're equal. That's the definition of surjective. Is that okay? Everybody happy? Okay. All right. So that's it. You show that if you have inverse, you can have bijection. Now assume bijection and let's do the proof. What's your first name? Hello. What was your first name? Renshu? Okay. Yeah, so let's do the proofs Renshu mentioned. So, but yeah, okay. So no, first I have to build the inverse. So just because you have bijection, it doesn't mean that inverse exists. So you have to prove its existence. Okay, too many words. So how do you do it? You have a map from V to W, and you know the guy is injective and surjective. So I need to build a map T inverse, I call it S, that goes from W to V in a well-defined way. Okay, what is well-defined means? So let me remind you the function test from high school. So this guy is not a function, right? Because it sends one element to two, right? So this is the function test, right? So that's how you show well-definedness. You need to show that one element gets sent to one element. So take any W in W, and you need to define how S will act on it. So anyhow, yeah. So T is surjective. So W is in the image of T. Okay. Let me do it in steps. So step 1, step 2, step 3. There exists X in V such that W is TX. That's the definition of being in the image. So then for let X, or let me say it this way, let SW or T inverse W be defined as X. Because then what does it do? If you plug in, because indeed, then you have the T of SW is W. Right? So it acts as the inverse. And then you might ask, well, how do you know this X is unique? Now you have to use, so how do you know that this X is unique? Well, suppose there was another one. Suppose there exists YV such that W is T of Y. Well, then let's do what Rishon mentioned. So you have TX is W, and this guy is also W, TY. Now you take their difference. And you get T of X minus Y is 0. Right? But then T is injective. So what do we know about its kernel? Do you guys know? What's in the kernel of an injective map? It's just a 0 element, yeah. So T is injective means kernel of T is just the 0 guy. So X minus Y is equal to 0. So X is Y. So there's only one choice. So it passes the function test because it maps W to a unique element X. You don't want to have the situation where W gets mapped to X and Y, because then it will fail the function test. So that doesn't happen here because X is Y. Okay, so that's how we build the inverse. You need bijection. Okay. Is that okay? All right. Yeah, all right. If you have a question, just tell me. So we build our inverse, and yeah, by injectivity, you have that it passes the function test. All right. Now let's show that it's linear. So I have to show that take S A W1 and then W2, that this is equal to A SW1 SW2. So that's what we're going to show. Yeah, I wanted to ask, but it might be a little bit hard. So, but yeah, let's do it. Let's see. So, what's a good way to do this? Okay, whatever. Let's see. So, right. So we have that SW2 is some V1 in V, and same thing for 2. So now the proof is kind of weird. You have to go back to the image. So you take these two guys and you look at their as inputs to T. So you look at this, and T is linear. So you have that this is A TV1, TV2. But then we know what V1, V2 are, called this star. So this is A of SW1 and TSW2. We said that S it's the inverse of T. So you get AW1 and and W2. All right, so what does that say? It says that since this guy has a pre-image, it implies that AW1, W2 is in the image of T. Okay. So let's parse this out. So since it's in the image of T, you can do the following. You can evaluate, this is a very perverse argument, but that's what we have. So that means S can act on it. So first, this is showing closure. Now I showed that this summation, once you map it, it's in the domain. Now you have to go back. I know it's very weird, but that's how they do it in the book. I have to, if I had another way, I would do it. So if we reverse all this argument, we showed that this is equal to A V1 V2, right? We showed that this is equal to this. Now take S of both sides. And you get this, right? So this was T and you took S. So this is A V1 plus V2. But then what is V1, V2? Is SW2, SW1. So you got the linearity. Is that okay? Does that make sense? What about you? Does that make sense? Okay. All right. What about you? Does it make sense to you? Okay. I know it's a weird argument because you don't have linearity for the inverse. So you have to go back to the linearity of T and then come back. But this is the last time you're going to see it because from now on, you can just assume S is linear. I mean, the inverse. So this weird sort of argument, you don't need it anymore. Because we did it for you. All right, so the inverse of a linear map is also linear. That's the lesson here. Okay, all right. Now, one of the most important results in this class is the following. So you give me any vector space. So, oops. So give me any vector space. I mean any, like polynomials, matrices. And if you have that its dimension of V is n, then you can map V isomorphically. There exists a map that goes from V to Rn. That's basically the result here. I mean, this is the generalization, what we're going to prove, but how we're going to use it next week and all the future weeks is mostly that that there exists a map that sends you to Rn. So all the vector spaces are basically Rn. That's all we're studying. So any finite dimensional stuff are just Rn. And if you go to statistics, that is very nice because you're just working with vectors. You can work like concrete vectors. Okay, anyhow, questions? All right, let's prove it. Yeah, so any vector V, we can map it to Rn. All right, so we assume existence of this map. We're gonna show that the dimension of V is equal to the dimension of W. Okay, that's what we want to show. Yeah, so let's see. Right, I do it both ways. So dimension of the image is equal to this. Now, can someone tell me how I go from left to right? What property are we using here? Here and in the chart. Can you just say the word? Yeah. No. Anybody? Yes. So here all we're using is that injective is the same as dimension, is the same as kernel of T is just the zero vector, which is the same as dimension of the kernel of T is 0. So all we said is add 0. That's what we did. So yeah, we're using injectivity here. And then Crucians, right? Crucian. Then this guy here is a rank nullity. Rank nullity says that the dimension of the domain can be split between the dimensions of the image and the kernel. Okay. Perfect. Yeah, so how do we finish the proof from here? How do we show that dim V is equal to dim W? What property do we use? Yeah, surjective, yes. So this by surjectivity is equal to dim W. That's it. Perfect. All right, now assume the converse and show that, want to show there exists an isomorphism. So iso between V and W. And this will be the construction of what we call a coordinate map in the case of WRN. But yeah, so please try. Yeah, if you don't understand some step, just let me know and I will go slow because this material will keep coming back. So it's the same stuff, same argument over and over again. All right. How do you do this? How do you build this map T? Just by knowing that the dimensions match. Well, dimension means the size of the basis is n, and also the size of the basis for W is also n, right? So you have V, and you can cover it with V1, V2, V3, and so on. And you have the same number of vectors in the image. Okay, and we want to build some T guy. So how do we do this? Well, you just build it on the basis. So you do the correspondence. Let me go up here. So you send V1 to W1. You send V2 to W2 and V3 to W3. So that's your mapping, okay? You just follow the index of the basis. Okay, so TV, you define the function to be sending the VIs to the WIs. Now I just told you how to make an array, but now let me ask you, we want more than that. We want to define our map with all X and V. So how can I define my X? So here and in the chat, can you tell me what should I put on the right? Yes. Yeah, so exactly. So X is equal to A0 V1, I mean A1, AN VN. And then we define this to be the, we define it to be A1 TV1, AN TVN, which is A1 W1 and AN WN. So that's our definition for T at other points. You just define it as the linear combination of the W's. Is that okay? All right, good. So that's it, that's our map. And you're gonna see this again and again. So when we have Rn, you will just take X from V to the standard basis. This will be A1, E1, AN, EN. That will be basically your, what we call coordinate map. So yeah, I mean, we can talk about this on and on. So, but this is the construction. That's it. All right. So we built a linear map T V to W. Now we want to show that this guy is bijection. And then that will show that T is invertible. Right? From before, all we needed was bijection in order to get invertibility. Okay. So injective. You take two elements and you assume that they're equal. Assume that they're equal. Want to show that even X will equal Y. That's injectivity. That's the contrapositive of injectivity. So just to remind you, either you go this way or you go the other way. Whatever you like. These are the same as injectivity. Okay, all right, good. Okay, so what's the trick? Right, so X and Y are in V, so you write them in terms of basis in V. So yeah, let me finish it from here. So what do we have? We have the T of X. No, let me do it this way. So summation of AK WK is equal to T of X, which by assumption is equal to Ty, which then equals summation of BK WK. Any ideas how to finish from here? Go ahead. Yeah, can you speak up? Perfect. Thank you. So you take their difference and it's 0, but the W's are Li. So you get that AK minus BK are 0. So you get AK is equal to BK. So that means that X is Y. So let me do it this way. So it's summation of AK VK, which is the BK VK, which is Y. Thank you. Questions? All right. If you have a question, just let me know. So we showed injective. Now let's do surjective. All right. Let's do it together. So what do I have to show? I have to show that if you give me any W, I can find some X that gets mapped to W. Good. So yeah, we know W is equal to C1, W1, da, 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 Cn, Wn. What do you think should be the expression for V? Any ideas? So that it will get mapped to W. Can somebody tell me what the coefficients will be for V? Here or in the chat? You can just say, the coefficients will be, What are the coefficients? A1, what is A1? Elizabeth, what is A1?
I don't know, just any constant.
Yeah, any ideas? Huh? What is it? Same, right? Yeah, so it will just be, I think that's what Elizabeth meant, right? You just meant C1. Yeah.
Yeah, just any
so
constant.
C1, V1, and then Cn, Vn. Why is that? Because when you evaluate it, T is linear, right? We just proved that. Yeah, we proved that it's linear. So this will become T of C1, V1, or let me say it this way, we defined it. So I think Krishan said that. We defined this to be C1 TV1 Cn TVn, which is equal to C1 W1 Cn Wn, which is what W is. Right? Okay. So you gave me an arbitrary W, and I found you some V that got mapped to it. So this is V. This is how we define V so that it will get mapped to W. That's it. So that means you have surjectivity. Is that okay, Kushan? No. Oh, because V is a subspace. So T, okay, I mean, this is what you said a few minutes ago, right? Let me go back to so how did we define X for any X in V? It was precisely so this was the definition. Okay, perfect. Is that okay? All right. Okay, so that's it. Surjective, and yeah, we already proved that surjective that bijection means invertible. So we showed in that dimension V equal W if and only if there exists an isomorphism from V to W. And iso means invertible. Okay, so you can go back and forth. There's some linear map that allows you to go back and forth. This is boring. This is amazing. Right? Because if you know that you have the map, then you just send basis to basis, so you will have n and n. But the amazing result is, if you just know that the size is the same, then you can have a linear map between them. I mean, that's stunning, but okay. And in the case of Rn, we're going to call this map coordinate map, and we will upload the nodes. There's some extra nodes. And this map T that we've been talking about In the case of W equal to Rn, we will denote it as gamma B. Okay, so this is the notation we're going to use in this course. And it's the map that sends you from V to Rn when dimension of V is n. Okay, and we just built this map. So this coordinate map exists from all this abstract construction we did with surjectivity, injectivity, T of X, and all that stuff. Okay. All right, good. So at least we covered. So yeah, I mean, up to now, this is basically the midterm. This was the cutoff. So the moment I hit coordinate map, that's the stop. So yeah, let's do some examples. Okay. I mean, I talked about it before, but let me remind you. So we had space of matrices, and the dimension of the space of matrices is equal to the dimension of the span of the following matrices. So you put 1 and 0 everywhere else, and you put 1 at the Aij place. Okay. Right? So this matrices where you put 1 only in one place gives you the whole space of matrices by linear combination. And there's n times n choices. So you have dimension of Mn to be n squared. Okay. Everybody happy? So from what we proved, so from ISO result, there exists a map called gamma B that sends you from Mn to Rn. And it's invertible. But this is an abstract construction, so I even gave you the I gave you a concrete construction. But okay, I mean, let me just say it here. So yeah, so if you give me any matrix, what did we do? You give me any Aij, then we map Aij to xk, where k is equal to I minus 1 n plus j. And I can also go backwards with modulo. So you give me k and you do modulo n. So this is j. So k is equal to I minus 1 n plus j. So this map goes back and forth. It's an invertible map, and it's the canonical map we will use from matrices to n square vectors. Okay, that will be the coordinate map. Is that okay? Do you mean Rn squared? Yes, that's what I mean. Yeah, that's what, it's not R2n. Oh, here, yes, Rn squared. Thank you. Yes, yeah, Rn squared. Thank you. Okay, let's do more examples to give you practice. Yeah, the derivative map. So the derivative map, it takes a polynomial of degree n. So a0, a1x, an xn, and it maps it to what? A1 A2 times 2 x an n xn minus 1, right? When you take a power of a monomial, the power comes down. Is that okay? Okay. Right. Can someone tell me if this map is an isomorphism between Pn and Pn minus 1? What's a quick reason to say no? There's a quick argument. One line. The what? Yeah, exactly. So what is the dimension of Pn? N plus 1. And the way you find this, let me just say it for people who don't know. This is the dimension of the span of 1 xn. And there's n plus 1 elements, which is strictly bigger than n. The dimension of span of 1 xn minus 1, which is the dimension of Pn minus 1. So there can never be any isomorphism. So that means if you have a map and it does something like this, it sends you some lower dimensional vector space, it's never invertible. So that's another quick way to check invertibility. Instead of checking injective, bijective, like we're taking two vectors and comparing them, we can use this machinery to say, oh, dimensions are different. Done. Because the ISO result goes both ways. Perfect. Now, what about this map? So, yeah, I'm asking you too much. So I should do this. So, but what's your feeling? Is it isomorphic or not? I don't know. It's kind of hard to. So this map sends P to X times derivative of P plus the polynomial. Do you think it's isomorphic? Not isomorphic? Your gut feeling. Like, what do you think is the degree of this one? Huh? Can you speak up? Yeah, it's still n plus 1. Why? Because for one thing, you added this. And, in fact, I'm thinking, do I need to add? Oh, I need the constant term. Yeah. So, yeah, this is a little bit tricky. But yeah, so do I go over it here? Yeah, let me do it. But do we have more interesting examples? That's all right. Let's do this one. Because there's some questions that might show up that look like this. So let me do it. So what do I want to talk about? I want to show invertibility. All right. So the quickest way is to do a biject. All right. So you just have to show bijectivity and right. And can someone tell me when you have V to V and you want this to be bijective, what is the simplest criterion to show that? So we proved this. I just want to see if you remember. There's one thing you have to check and you're done. When the spaces match. So this is, you can just use one word in the chat. So it uses a lot of machinery. So that's why I'm asking. So the dimension of what? Kevin? No, we're talking about that T is bijective. So how would you show that T is bijective? There's a quick way to do it. Okay, let me just say it because we run out of time. We just have to show that the dimension of the kernel of T is 0. So you just have to show injective. And the reason is rank nullity. So, you know, let me do it this way. So dimension of image T plus 0 is equal to dimension of V by rank nullity, right? But this V is the codomain of the map. So that gives you surjective for free. So just by showing injective, you get bijective. Is that okay? Everybody happy? All right. So anyways, we'll continue. Okay, thank you. I'll stick around for questions. So if you have a question, okay, yeah. If you have a question, just let me know and I will answer it. So you can use the mic if you want.
Hello, Professor.
Hi.
I just have a question about the midterm for Friday.
The midterm, yeah. What about the midterm?
I know there's a second part, 1 hour where we should write long answers, right?
Yes, you have to write long answers.
Can you write on a copybook, then we take a photo and send it to Gradescope?
To do what?
To answer the last part, the second part of the exam, because there are long answers.
So then what do you
how
want?
are we gonna type our question? Type in our answer.
No. It's gonna be on Gradescope.
So I can write on a paper. I take a photo and send
Yeah.
it?
Then you upload the picture on Gradescope.
Okay, good. And last thing, when I've been like studying for this course, studying for the midterm, I've really had a problem with making an efficient strategy to study for proofs. You have an idea? What's a very good way to do it? To learn about
did you
proofs?
see? I made a post on Piazza about proof techniques.
Yeah.
Can you read that first, and then we can talk more? Like I gave some strategies
and just
on.
last,
Yeah.
okay.
Go ahead.
The main proof that I should like understand are in the slides, right?
Well, the main thing is you do the problems, and then you have the priority are the problems we assigned you. Then what we do in class, and finally the book.
Okay. Thank you so much. And if I have a question about the correct answer for a suggested problem, do I come to Piazza?
Yeah, or office hours, yeah. Any more questions? No? I'm still here if you have a question. We're not getting kicked out. No? Okay.
Oh, sorry, Professor. Hello?
Oh yeah. Why do you wait till like the when
No, sorry, my mic wasn't working. I'm so sorry. I don't know technology.
put it in
happens.
the chat? We can talk in the well, yeah, go ahead. Yes.
My hands. I'm really sorry. So this is mostly regarding the homework. So basically, to prove that it's like to prove that something is a subspace, right? If it's already a subset of a bigger vector space. So we already went through that, and the fact that you can just show closure, right?
Yes.
And that's what I saw in lecture. Now, for the homework, I did show closure, but they gave me a comment that you also need to show that your like the set is non-empty. But I thought that was kind of trivial because we're already like a subset, right? Like, so how can it be empty? So that kind of confused me.
You already know the set.
Like, okay, so let me be like, I guess, clear. So this was to show that a set that is already the intersection of two other subspaces is also a subspace, right?
Uh-huh.
So just because, like, trivially, because it's an intersection of two subspaces, and subspaces always have the zero vector in them.
Oh, I see.
So
Yeah.
it's
Well, yeah, that's the
intersection of-
proof. I mean, that the subspace, you see, it's kind of tricky, right? We proved that the zero of the larger space is the same as the
Is in
zero.
the-
Huh?
Yeah.
Yeah,
So, but my question.
but it's a proof
to
thing.
write-
It's not immediate that, you know, it's a comment. It's like a short comment that it's non-empty because they both contain the zero, the identity element.
Oh, so I have to write that. Okay, I guess that was my entire question. And so just regarding the, I mean, that being said, regarding the last thing that you did, so the fact that if you're going from the same domain to the same codomain, like, you know, V to V,
Yeah.
that you get basically surjective for free when you when you
Yes.
prove injective. Can you just like re-explain that really quick? Sorry.
Yeah, that's fine. Yeah. Let's see. So injective means zero kernel. And
Can we use that like just as is? Can I just write injective means that the kernel is just zero, or do I need to do some proof for that?
no, we proved that in class.
So that's okay.
Yeah. So injective, we proved is the same as we proved that it's the same as the kernel is just the zero guy, which means that by definition it has zero dimension. And then rank nullity says this, right? Hello?
So that okay. Yeah, yes, I'm still here.
Like a dimension of image plus dimension of kernel as the whole space, right?
But here the V is technically the domain we're talking about, right?
Yeah,
Like,
yeah, but
the V as the domain.
that's why it
No,
works.
I know they're the same. Yeah, I know there's okay.
Yeah, so in a way, this is V, which is W, because they're the same space, because V is W, if you want to do it that way.
But okay, like okay, I guess the dimension of the and then so the image of T, that would be the I guess, so we're showing that technically the image of T is equal to the dimension of V itself, right?
Yeah,
That's what we're proving.
so we also
Like, that's what
showed
surjective is, right? Like
surjective,
surjective
yeah,
is that
it
the
means-
dimension of the
so
like it means that
surjective
the
means
oh, sorry.
image of T is exactly V.
So not just the dimensions, just the actual
Yeah, yeah,
sets?
but we proved in class that when so the general result that we proved was that if you have that S is a subset of V, then S is V if and only if dimension of S is dimension of V.
Oh, so the subset parts we're already kind of taking for granted because, like, you know, it's like literally in it. So I guess, okay.
Yeah, exactly. Yes. So we already know that the image of T gets mapped to V.
Okay.
And we have that the dimensions match, so we get the whole thing that image of T is V.
Is V. So that's the actual solid thing for surjective. Like the actual set is equal, not just the dimension.
Yes.
I see. Okay, that makes more sense. I guess that didn't connect for me. Okay, thank you so much. Sorry for keeping you after class.
No,
Have a great
it's
day.
fine. Yeah, yeah. Okay, good.